Welcome to INSITECT. Today we are talking about network fundamentals, the invisible infrastructure powering modern security. When you really look at the infrastructure that runs, well, everything in modern society, from the simplest door access control to the most sophisticated cloud analytics, it all comes down to the network.
It really does.
It's the absolute foundation. If that plumbing breaks or if the foundation is compromised, every single critical system just fails. And we're not talking about, slow Wi-Fi.
No.
We're talking about the collapse of surveillance, supply chain management, and yeah, every single cybersecurity defense we have. It all relies on that underlying connectivity.
It is the highest single point of dependency in any modern enterprise. And this is why for any analyst or engineer who's worth their salt, you just cannot effectively analyze a vulnerability or design a defense in-depth strategy if you don't fundamentally get the core mechanisms.
The things that actually move the data.
Yeah, exactly. Our mission in this deep dive is to uncover those core mechanisms, protocols, switching, routing, but we're going to focus on how they dictate not just reliability, but vulnerability. The way a network is built for reliability is precisely what creates the attack surfaces we have to defend.
Okay, let's unpack this starting with the scope. I mean, we have to define the boundaries before we can even talk about securing them. We usually categorize networks by their scale. The most familiar one is the local area network, the LAN.
Right, your office, your building.
Exactly. That contained environment.
Yeah.
A single office, maybe a data center or a university campus.
And that LAN is what connects us to the bigger world, which is the wide area network, the WAN. The WAN spans, immense geographical distances, using complex carrier services to connect different LANs across continents.
And sometimes you hear about the one in the middle, the MAN.
Yeah, the metropolitan area network, for citywide scale. But the critical implication here is pretty simple. The further you move from your LAN out into that WAN, the less control you have. You become totally dependent on third-party security.
And that whole structure LAN versus WAN, it's all defined by these conceptual models that let devices from different vendors actually talk to each other. We rely so heavily on models like OSI and TCP/IP, which, separate everything into distinct layers.
They do, but for security analysts, I think the most critical division to understand is the split between Layer 2 and Layer 3.
Okay, let's dig into that.
Absolutely. This distinction is paramount. At the data link layer, that's Layer 2, we are dealing with unique, hard-coded 48-bit AMI addresses. That is purely for local hop-by-hop delivery inside the same network segment.
So just getting the data from my PC to the nearest switch.
That's it.
So if Layer 2 is only local, why does a global security analyst even need to worry about MA addresses? I mean, doesn't the router just handle that once a packet leaves the building?
That is the key question. While Layer 3, the IP layer, handles the global journey, Layer 2 is where all the local mayhem happens. MAC addresses are essential because Layer 2 is the domain of broadcast traffic, and therefore attacks like ARP poisoning, ME flooding, and VLAN hopping. If you don't monitor Layer 2, an attacker is basically running free inside your network before their traffic ever hits a secure router or a firewall.
So Layer 2 is the local ID, and then the network layer, Layer 3, that's where the logical IP addresses come in. These are the addresses that determine the final end-to-end path across maybe dozens of different networks. This is where global routing happens.
And we also see these architectural models that define risk. You have the classic client-server model, great for centralized control, applying security policies, but
a single point of failure.
An unavoidable single point of failure risk. Then you have the peer-to-peer model, where resources are shared directly. It avoids that central failure point, but from a security perspective, in a large enterprise, it's a massive headache.
No centralized logging, inconsistent patching.
Yeah, just poor policy application all around.
Yeah.
That decentralization becomes its own vulnerability.
So if the model defines the rules, the physical layout, the topology, that defines how the network responds to a failure. We mostly see the star topology in modern LANs, right?
Right. Everything connects to a central switch.
It's easy to troubleshoot, but the security implication is that central switch is now the highest value physical target for anyone wanting to cause disruption.
And when reliability is absolutely non-negotiable, you move away from that simple star. In core network backbones, where downtime is just catastrophic, we see the mesh topology. It offers incredible redundancy because every core device is connected to multiple others.
But that sounds expensive and complex.
It is, which is why in most big enterprises, you see a hybrid design. You'll have a redundant mesh core connecting to distribution switches, which then feed out to the star configurations where the end users are.
You mentioned redundancy, and that brings up complexity. Network loops, for example. If someone just plugs two switches into each other by accident,
Yeah.
that can create an infinite broadcast storm and just kill the network.
Kills it instantly. Exactly. And that brings us to one of the most critical protocols for high availability, Spanning Tree Protocol, or STP. Yeah. Its entire job is to detect those redundant paths and logically block one of them.
So the path only becomes active if the main one fails.
Precisely. But here's the security insight. STP can be manipulated. Forcing an attacker's device to become the root bridge is a known, dangerous man-in-the-middle attack. You're hijacking the network's own resilience mechanism and turning it into an attack vector.
Wow. Turning a failsafe into a failure point.
Yeah.
Okay, so the devices themselves execute all this. Let's define the difference between the main ones.
Think of it this way. Switches operate at layer 2. They're like the postal workers inside one big office building. They look at the MSC address, and their job is to forward traffic only to the specific port where that device lives.
So it's efficient. It keeps broadcast traffic contained.
Very efficient. And then you have the router. It operates at layer 3.
The gatekeeper.
Yes, the gatekeeper. It uses IP addresses and complex routing tables to find the best path between different networks. It's more complex, can manage its policy, and because of that, it's a much higher value target for attackers.
Now let's get into the actual language of the data, the protocols. At the transport layer, we immediately hit this big trade-off: reliability or speed.
This is the essential dichotomy of TCP versus UDP. TCP, Transmission Control Protocol, is all about reliability. It's connection-oriented, it uses a three-way handshake to set up a session, and it uses sequence numbers to make sure every single packet arrives in perfect order.
Which is what you want for web browsing, email, anything mission critical.
Anything where you can't lose data. But that reliability comes with overhead. It's slower, which is why we have UDP.
User datagram protocol.
Right. UDP sacrifices that confirmation for raw speed. It's connectionless, just fire and forget. It sends data with a minimal header, which means low latency.
Perfect for VoIP, video streaming, where a little packet loss is better than a long delay.
Exactly. But for an analyst, that lack of confirmation is also critical because UDP is often leveraged in DDoS amplification attacks. The attacker doesn't need a persistent connection to just flood a target with junk traffic.
It's pretty amazing that even as we scale networks up to, say, 400 gigabit links, the foundational standards like Ethernet, IEEE 802.3, stay consistent.
The frame format is the same, but the research is clear. You can't cheat physics. To get that 10 gigabit performance over the full 100 meters, you absolutely need Cat6a cabling. Anything less is a bottleneck.
And that scaling issue brings us to probably the biggest challenge the networking world has faced: the addressing crisis.
IPv4, the 32-bit address space, gave us about 4.3 billion addresses. We ran out years ago.
I remember when that started happening, it was just chaos. Forensic logs suddenly made no sense.
Precisely. That scarcity forced the invention of network address translation, or NAT.
Yes.
Specifically port address translation. It was a hack, really.
A necessary one.
A necessary hack that allowed hundreds of internal private devices using ranges like 10 dot or 192.168 to share a single public IP address. It saved the internet from collapse, but it made forensic tracing incredibly difficult.
So the temporary fix became this permanent layer of obfuscation. What about the long-term solution?
The long-term answer is IPv6. At 128 bits, it offers an effectively unlimited address space. And, crucially, it was designed with security in mind, with native IPsec support built in. But the transition has been agonizingly slow. Most places are running dual stack now.
Which just adds more complexity for analysts to manage.
It does. Two parallel address structures.
Okay, we've built up this complex stack of layers, protocols, addresses. So here's where the critical analysis comes in. Is this layered approach truly secure? Or is all this complexity just creating more attack vectors, more places for attackers to hide?
That is exactly the right question to be asking. The complexity does create opportunity, which is why we have to preach defense in depth. Relying only on a perimeter firewall is, frankly, reckless, especially for containing an attack once it's inside.
You have to build security into the switching and routing fabric itself.
You have to. The primary tool for that internal defense is the VLAN, the Virtual Local Area Network. VLANs logically segment a physical network. You can isolate employee workstations from servers or keep your security cameras and guest Wi-Fi separate.
So if someone compromises a guest's phone, they can't immediately start probing your critical servers.
That's the idea. It provides layer 2 isolation.
But that isolation breaks down the minute those segments need to communicate, right?
It does, and that's the crucial point. While VLANs give you that layer 2 segmentation, Any traffic moving between them, what we call inter-VLAN routing, must pass through a firewall for real security control.
You can't just let a layer 3 switch handle it without scrutiny.
Never. And if you're still using basic packet filtering firewalls that only check ports and addresses, you are missing the attack. You need next-generation firewalls that add application awareness and deep packet inspection to see what the data is actually doing.
And beyond the big central firewall, you need security at the edge, right where users plug in. Research shows that just locking down the physical ports is a huge first step.
Oh, absolutely. We rely on low-level techniques. Things like port security, which limits the number of ME addresses on a port, maybe locking it down to just one authorized device.
So an attacker can't just unplug a printer and plug in their laptop.
Exactly. Then you use DHCP snooping to stop rogue servers from handing out bad IP addresses, which is a classic way to start a man-in-the-middle attack.
And what's the most critical vector there?
Dynamic ARP inspection, or DAI. ARP poisoning is devastating. It fools devices into sending their traffic to the attacker instead of the real gateway. DAI actively blocks those spoof packets. You couple that with 802.1x authentication, which verifies the device's identity, and you have a really robust edge.
And we can't forget wireless. If the wired network is locked down, wireless needs to be even tighter.
And the standard for enterprise wireless has to be WPA3. It replaces the old, vulnerable WPA2 PSK by using simultaneous authentication of equals. It gives much stronger protection against offline password guessing attacks, which are surprisingly effective against WPA2.
So if your organization is still on WPA2, that's an unnecessary risk.
The huge one.
Okay, so let's get into the real world. You're an analyst, the CEO is yelling that the network is down. Where do you even start with all this complexity?
You don't jump to the application. Good analysts follow a systematic process that rigidly follows the OSI model from the bottom up.
So check the physical connection before you start digging into complex routing tables.
Precisely. Is the cable good? Is the switch port light on? That's layer 1. If that's okay, you move up to layer 2, then layer 3, and so on. It stops you from wasting hours on a server config when a fiber link is just down.
And the everyday tools, ping and traceroute, are still incredibly powerful for just basic connectivity checks and path mapping, but for a real deep dive.
You need more. You need protocol analyzers like Wireshark for deep inspection of the raw traffic. Sometimes analyzing the frame itself is the only way you'll find a subtle attack.
We're also seeing a huge push toward proactive monitoring, right? Using systems like SNMP and NetFlow.
Yes, and they're essential for establishing baseline measurements. If you don't know what normal bandwidth usage looks like at 10 a.m. on a Tuesday, you have no way of knowing when something is wrong. Baselines are your early warning system.
They trigger the alerts.
They do. And the final lesson we always come back to, and it's not technical, but it's critical, is the value of documentation and change management. Having accurate records and tracking every single modification is essential for rapid recovery.
A change made 6 months ago is probably more likely to be the root cause of an issue than some new zero day.
Far more likely.
So when you put it all together, we rely on this staggering complexity, but that complexity also provides resilience. And here's the provocative thought for you to consider. The distributed nature of routing means that decisions happen independently at each hop.
Every router for itself.
A packet going from London to Sydney might cross a dozen routers, and each one makes its own forwarding decision based only on its local information. This distributed system is why the internet is so resilient to local failures, yet it's also what makes tracing the full path of a sophisticated attack so profoundly difficult to map end to end. Thanks for listening. We will continue to talk about security and technology. See you in the next episode.